Okay, yeah, back to the question. So, so the question wants you have a disk with surface charge density sigma, and you're supposed to figure out the electric field at a point uh, z away along the z-axis from the disk. Okay. Now, let me do this problem. Basically, what a disk is just a bunch of rings. So it would be better if, and you know, the question first should be that is to figure out the electric field along a disk, along a ring, and then use that in order to uh, uh, just divide the disk into rings and integrate to figure out the electric field away. So let me show you the ring first. So let's consider the ring. So we have a ring and of radius r. Okay, and we want to find the electric field at distance z away. So this is the z-axis. Okay, and let's assume that this disk, this ring has a radius r. Right. Okay. So, and this is point P here, let's say. Okay. So we know that the electric field is equal to 1 over 4 pi epsilon integral of lambda dl, right? Lambda dl prime, lambda, and lambda is a function of r prime. This is, oh, by the way, the disk has a surface charge or a linear charge density lambda. Okay, lambda r prime over the separation vector squared in the direction of the separation vector dl prime. Fair enough? Okay, so yeah.
It makes it simpler because if it's along the central axis, then the only field we have to worry about is up or down. The sideways components cancel.
Yeah, exactly. So if you were to take a point here, like this is, say, your dl, yeah, and then you join it to the point, yeah, this is going to be your separation vector pointing in that direction. But then there's another one from this side, right, going the other way, and therefore the x components from the red one will cancel the x component from the green one, because the green one's x component goes to the right and the red one's x component goes to the left. Therefore, these components cancel each other out, and you can make this argument all the way around the ring, because every point will have its corresponding image and will therefore cancel its x component and y component respectively. And the only thing that will survive is the electric field along the z, right? Yeah. So okay. So let's call this. So let's call this angle here theta. And we know that from the geometry of the figure, this distance here is z. So pi separation vector square is equal to r squared plus z squared. Okay. And we know that cosine theta is just z over r. Sorry, z over this, which is z over r squared plus z squared. Okay, now lambda is constant, so we can pull it outside the integral. So E becomes 1 over 4 pi epsilon lambda integral. So I'm integrating along the disk. So I'm going from 0 all the way to the circumference of the disk, which is 0 to 2 pi r, right? dl prime over r squared plus z squared. But r squared plus z squared is constant, so I can pull it out. And I have no denominators here. So then what I get is, oh, there's a z here too. And this is all we said in the z direction. So then that means the electric field for a disk turns out to be lambda z over 4 pi epsilon uh, uh, oh yeah, we forgot the cosine theta term because you are talking about the z component, yeah? So technically we'd have to multiply this whole thing by cosine theta in order to capture the z component of the electric field, and cosine theta is just z over r squared plus z squared. We already have the z. This was the z that's in the cosine theta over z squared plus r squared to the 3 over 2 times 2 pi r times 2 pi r, and this is all in the z direction. So this here is the electric field for a ring of charge. Okay, this is for a ring of charge with linear charge density lambda. Okay, let me get back to the question at hand now, which is that of a disk. So I'm going to break up the disk into rings, each of radius r. Right? So now I will consider the disk case. So you know, if you have this disk, you can break it into rings. So let's say that this is the z-axis, right? And so I could break this up into thin disks of radius r. Okay, and the thickness, I have some thickness to this, dr. So I mean, I'm exaggerating it here a little bit, but this here is dr, right? So I take the electric field of each ring, right? Now, what's the total charge of a ring? So the charge on the ring, so now Coulomb's law reads it's sigma r prime, right, over separation vector square dA prime. Okay, so the charge on the ring so this ring has, by the way, a sigma surface charge density. That's coulombs per meter square, right? So on each ring there's sigma, right, times, so that's coulombs per meter square. And then, of course, if I want to figure out how much charge is on that specific ring, I'd have to multiply it by the circumference of the ring, because I have to go, you know, because it's just a bunch of rings. So I go around one complete circle. So I multiply that by meter, which is 2 pi r in meters. So that gives me coulombs per meter, because meter cancels meter. Okay, but I still have to multiply it by the thickness of the disk, which is also in meters, which is dr. So this is going to be the charge sitting on the disk. Okay. Okay. So now so the E for each ring, as we did in the above question. Okay, so I would replace lambda. Remember lambda? This guy here? I would replace that lambda now by sigma dr. You know, which makes sense because the units are consistent as well. It's charge per meter square times meter gives you charge per meter. So, right. So I would replace lambda by sigma dr in the above formula. So I will get the E for the ring is equal to sigma dr for lambda times the rest is the same, 2 pi rz over 4 pi epsilon r squared plus z squared to the 3/2. And now I can integrate this because this is just one ring of radius r inside a disk of radius big R. So I can take, so the E for the ring, the E for the disk, sorry, will just be sigma is constant, so all the constants I can pull them out. 2 pi sigma z times 1 over 4 pi epsilon, and then I can integrate all the rings starting from the center all the way out to r, the radius of the disk, r over r squared plus z squared to the 3 over 2 dr. Yeah, this is a fairly straightforward integral. This is u substitution. U is r squared plus z squared. So du is 2r dr. Divide by 2. Du over 2 is r dr. So so this becomes, so let me do the integral. So 0 to r over r squared plus z squared to the 3/2, right? This is equal to let me just keep it here. So okay, so now let's change the bounds of integration. If r is 0, u is z squared, and if r is big R, u is r squared plus z squared. So now this goes to, so the integral becomes z squared to r squared plus z squared, half du over 2, you bring half out, and then we get du over u to the 3/2. And this is a straightforward simple integration. You get 1/2 u minus 3/2, so add 1, you get minus half, and divide by minus half, so those two go away, so you get 1 over square root u, right, from z squared to r squared plus z squared, and then the upper bound, so 1 over r squared plus z squared. Oh wait, I forgot the negative, yeah? Yeah, so I can flip them. So this is 1 over z minus 1 over r squared plus z squared. And so now I can plug it into the electric field formula. So we have E equals right? E equals 1/2, the pi goes away, So we get sigma z over 2 epsilon 1 over z minus 1 over r squared plus z squared square root. And of course this is all in the z direction, because again you can make the same argument that you made on the ring, you can make it on the disk. Every ring with its corresponding x and y components will cancel out from 2 points that are symmetric with each other, so the only component that the integral picks up is the z component. And so this will be the electric field along at a distance z on the axis of the ring. So you could just use the ring to figure out the disk. Yeah, and you can just integrate the electric field of the ring. Yeah, because a disk is just a bunch of rings, infinite amount of rings lined up around each other.